Hey, Flipped Chemistry, how you doing? You ready for another lecture? I am too. Let's get into it. We're talking today about family traits and periodic trends. We're talking about the periodic table, but I couldn't resist. Here's a picture that shows a family, and you can see similarities in every family, right? Whether it's people or dogs or guinea pigs or atoms. And we're going to be talking about characteristics that are shared across a family of elements in the periodic table or across or trends that happen across a period in the periodic table. So I felt kind of crazy as I was putting this together. There's some humor in here, but that is a good thing. So here we go. Certain characteristics are predictable as you move across the periodic table of the elements, and so we call them periodic trends. And it's actually why the periodic table is called the periodic table, and it was initially why the rows were created the way that they were, was that mass grows across the row, and then they would say, hey, look, this thing behaves like this thing. And they would put the second thing under the first thing and say, it acts like that. And so it was the periodical repeating of chemical properties that caused the periodic table to be arranged the way it was initially. And then we refined it a little bit so that it reflects electron orbitals, as I showed you last time. So we're talking about the things that happen over and over and over again as you go across the table. One of those is that atomic radii gets smaller. And at first you're like, what? They get smaller? I thought that there was more atom there. There is. There's more stuff. There's more protons, probably more neutrons, and there's more electrons as you move across the table. So why does that get smaller? Well, electrons and protons like each other, right? They're opposites, and opposites attract. So the more positivity you have in the nucleus and the more negativity you have in the cloud, the more the cloud wants to hang on to the nucleus, and the nucleus wants to pull the cloud closer to it. And so that attraction between more positive and negative makes the electrons move closer to the nucleus and makes the atom as a whole shrink. Kind of cool. But then when you start over on the next row, it gets bigger again. And the reason for that is we've added another shell, right? Row 1 is electron energy level 1. Row 2 is energy level 2. So 1 can get smaller, but then you add 2 to it. And then 2 can get smaller, and then you add 3 to it. And 3 can get smaller, and then you add 4 to it. So it keeps getting bigger as you move down, but it gets smaller as you move over. Let me show you a picture. Here we have row 1, lithium, down to fluorine. And you can see the diameter here in nanometers. These are very small. 0.152 nanometers for lithium, 0.064 nanometers for fluorine. But fluorine has 7 electrons, and lithium only has 3. But it is, very, very small. It's only 60. No, it's less than half the size of lithium. So we've got a trend here that initially doesn't make sense, but when you understand the attraction of electrons to protons, it does. And then as you move down the row, these all get bigger as you move down. They get bigger as you move down, but they get smaller as you move across. Okay. Another one is ionization energy, and that term means how hard is it to pull off an electron. Well, some atoms want to give away their electrons, especially in groups 1 and 2. They're like, here, take this thing. I don't want this, because we'll get to it later, but they want a full energy shell to show. And they've only got one stupid electron floating around on the outside, so they're like, yeah, ditch that, I don't care. And they want to show the full electron shell underneath. So families 1 and 2 want to get rid of these electrons that they've got, and families 6 and 7 want to grab electrons, and they certainly don't want to give the ones that they have away. So as you move across the table from left to right, you'll find that ionization energy increases. It's easy to get rid of electrons at the left end of the table. It's hard to get rid of electrons at the right end of the table. Electronegativity is the exact opposite. Ionization energy is how much do you want to, how hard is it to pull one off? Electronegativity is how much does it want to hang on to the ones it has, right? So on the left side of the table, very low electronegativity. Get rid of this thing. I don't want it. You can have it. Over on the right side of the table, I want it, I want it, I want it. It's my precious, would Gollum say, right? Okay. So the electronegativity increases, and ionization energy increases as you go across the table from left to right. Let's look at some pictures for this. Here is ionization energy, and this is the atomic number. So here, hydrogen doesn't really want to get rid of its electron. It's the only one that it has. But you can get it off of hydrogen. Helium is much harder to pull an electron off of because it's full. It's happy. Here, lithium will give it away. And then as you move through the periodic table across the row, neon doesn't want to give it away. It's very hard to pull an electron off. Sodium will give it to you. And then you move across the column and you get to argon, and it's hard. And then potassium, and then krypton. So you can see here are the family 1 elements, okay? Here are the family 8 elements. So mercury doesn't really belong there, but xenon and then radon, right? So these are the noble gases. These are the ones that don't want to get rid of electrons, and these are the ones that would love to give it to you. And again, if I just superimpose a periodic table over this, you can see here's the start of row 1, here's the end of row 1. Here's the start of row 2 and the end of row 2, right? Here's lithium, here's neon. Here's the start of row 3 and the end of row 3, sodium and argon. And then the next one down would be xenon, and then krypton. And then, so the noble gases show up as the peaks, and the alkali metals show up as the troughs. Pretty cool. Electronegativity works very similarly. So this is how much does an atom want to hang on to its electrons. And you can see that as you move across each row, the things tend to get taller as you move across the row. They also get taller as you move up towards fluorine. Fluorine is the highest one. So this is all kind of like a mountain that peaks at fluorine. And down here, these are all very small little hills. These guys don't really care if you take their electron. As a matter of fact, they like to give it to you. Okay, so electronegativity and ionization energy both increase as you move from left to right. Family traits. Groups are the columns, periods are the rows. So we were talking about the rows. Now we're going to talk about the columns. And so section 5C in your book has all the families. I'm just going to show you 4 of them, and you'll get the idea of what we mean by a family trait. A family trait are chemical properties that are shared down a column in the periodic table. Here's an example. Group 1 alkali metals form +1 ions. They give away 1 electron. They react violently with water because they find that water will accept its electrons and will change in response, right? And release hydrogen gas. And they are great conductors of heat and electricity. You put any of these soft metals in the fire and the heat moves up real quickly, and they'll also be good conductors for wires. So families share traits, right? Families share traits. Let me just give you a few examples. Here's a family that shares some traits. Oh dear. Here's another family, and these are sisters going to a dance. And they all have their chicken. I don't know if the chicken is the date. Oh, crazy people. Here's another family, and they share the traits of really big hair. Even the dog and cat share the traits of really big hair. And then, I don't know, dad's not too exciting or something. Here's another family trait. Families share traits. Okay, now back to chemistry. Here we go. This family shares traits, right? Lithium, sodium, potassium, they're all in group 1. And they are all shiny metals. And they all react with water and with air, and so we like to keep them under oil because it keeps them from reacting with the air. Okay, and they are very easy to cut. You can cut them with a knife, with a butter knife or a Swiss Army knife here in this particular picture. Here's kind of a funny one. Alkali metals are shy, but everyone desires to be around them because they're very attractive. They're also incredibly sweet due to their positive charge. I don't know what prompted somebody to do that, but if that's your picture, God bless you. Okay, this is kind of a cool thing. This is a picture of alkali earth metals reacting with water, and I couldn't resist. I'm going to show you somebody else's YouTube video, so just for copyright stuff, this is not me. You can watch this on your own, but I'm going to watch it with you because it's pretty cool.
Now let's see another reaction of the alkali metals, the reaction with water.
Oh yeah, let's watch it.
We'll start with lithium.
So
the metal floats on the water.
It steams, right?
With it, giving off hydrogen gas.
It's kind of fun.
Now
This
for
is even
sodium.
better.
The same sort of thing happens, although the reaction is a bit more vigorous.
And sometimes it
All
burns.
the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame.
Right, so the
The heat
potassium,
given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a light.
it's getting more intense as we go, right, as we move down the
The
column.
next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group.
More terrifying. I love it.
Let's try cesium, our fifth alkali metal.
I love it. I love it. And now you can understand why they didn't do francium, because that would have blown up the lab, right? So as you move down the column, the same chemical traits happen, they just get more intense. And so alkali earth metals group 2, very similar to group 1. They're more dense, they're less reactive. They form +2 ions, and they do burn, but you've got to get them really hot for them to burn. So things in this group are beryllium through barium, and they burn. These guys also react with air, so we tend to keep them under oil, just like we kept alkali 1, family 1 elements under oil. But magnesium will burn in a lab, and it burns really hot and bright, and it's kind of cool. Halides group 7, going all the way to the other end of the table. Halides group 7 are hungry to get one more electron, so they're very, very reactive. This is the most reactive group on the table. They form a -1 ion. They suck up one more electron and become -1. They're usually found as the negative part of a salt, is where you're going to run into these. Sodium chloride is the common example. They glow, and so we can use them in lamps. If you pass an electric field through them, they glow, and so sodium lamps are something that you'll see. Sorry, I just said sodium. That's not group 1. The halogens, like fluorine, chlorine, iodine, those things. They're poisonous in pure form, and so they will kill you, which we use that on purpose, right? Chlorine is used in pools to kill bacteria and algae and things of that nature. Here's some pictures of halides that have been crystallized. This is like naturally occurring ore salts that are made up of halides. This is a lamp that has halide vapors in it. Okay, chlorine gas, like we said already, will kill you. And this is an example of, unfortunately, it being used in World War II. The Nazis used chlorine gas against their enemies and also against people in concentration camps. It was the way that they killed their prisoners in those terrible places. Noble gases, group 8, last one. Group 8 is the elements that have a full valence shell. So they don't want any more electrons. They have all that they need. They don't want to take any more. They don't want to give any away. They just want to be themselves. They are called noble because they're non-reactive, and noble is like, I'm above it all, right? They don't do chemistry. Full valence electrons, they will not readily form an ion. They're easy to get to glow with an electric current. Most of the neon signs that you see are noble gases. Neon is one of them. And they are radioactive, a couple of them. And so those are the characteristics of these gases. Here's some pictures of them glowing. Helium, neon, argon, krypton, and xenon all glow different colors when you pass electric fields through them. So when you see signs like this, the espresso sign, or like this one, those are all noble gases in a tube that we were just passing electric fields through, and they glow. Kind of a cool thing that they share in their family trait. And here's just a funny cartoon, neon, noble gas. You're all just wannabes. Everybody's trying to give them their electrons, right? And they're like, no, you keep them, I'm good, right? Another kind of joke, helium, I can't bond with, well, anyone. Hope that's not your problem. If you have any problems or any questions, go ahead and put them in the comment field below. I'll try to get to them as soon as I can, or I'll see you in class tomorrow. God bless you. Have a wonderful night. See you soon.